In this lecture, we turn to another important topic, and let me just say at the outset that one of the challenges in learning and teaching this course in Geotechnical is that there are a lot of big, important topics which don't always directly relate to each other or build on each other very well, that you have to learn up front in order to understand everything else. For example, the last time I talked about effective stress, which I won't really get into until the next lecture. And this is one reason why you'll see soil mechanics textbooks take divergent approaches on what order to take all this stuff in. Well, that's pretty much the problem we have today. This is a very specific topic, and yet this is a very important topic. It is soil composition. We've talked about soils as a granular substance, and that granular substance has some major impact in terms of how we treat them in terms of their basic properties. Okay, you always hear people talk about whether the glass is half empty or half full. And this is one of the favorite debates people have, and they don't really get very far. In soil mechanics, our approach is different. We don't debate whether the glass is half empty or half full. What we want to know is what's in it. It's full of something. The question is, what is that? In the case of this glass you see here, something I got off of Facebook many years ago, you've got half air and half water. Is the glass half full? It's full. But it's got half air and half water. And that's kind of the way that we deal with it. Weight-volume relationships are important in soil mechanics. We deal with moisture content, the unit weight or the mass, and specific gravity are important concepts, along with relative density. The soil is a collection of particles that do not form a totally solid substance. You remember when we started out, we talked about rocks breaking down to soil particles, and then large soil particles breaking down to small soil particles. And in any case, by the time you get down to the particulate level, soil is a combination of soil material, which is in the particles, air, and water. And the relationship between this combination defines much of what any particular soil can do to support foundations. It also will impact other things as well, as we'll see. So, talk about a phase diagram. You see here, up here in the corner, we talk about a collection of soil particles. Soils in a particular, and those particles can be large, like they are with gravel. They can be kind of in the middle, like they are with sands, or they can be small or really small, as they are with silts and clays. But they don't take up the entire space that they occupy. The soil is not a solid mass. Leaving aside the whole issue of the large amount of space between atoms, which we won't discuss. We have soil particles, and between them are these little things we call voids. And voids basically is the part of the soil mass that is not soil. It's not solid, or not solids. One thing we got to make sure is to make a distinction between soil, which is the whole 9 yards of soil, air, and water, and solids, which are just the solid particles. So that's an important distinction we need to make. And we need to, between those voids, and those voids can have air or water or a combination of that. And we're going to talk about what those combinations are. Let's get some assumptions and definitions. First, we're going to assume that the weight of the air is 0. It's not 0, we know that, but compared to water or the soil particles, which are only slightly denser than water, or they're denser than water, more than slightly actually, are compared to them, it's not going to really help much in the calculations to worry about the weight of the air. Let's put it that way. Second, a dry soil, a water weight in a dry soil, there's no water at all. In completely dry soil, all the voids are filled with air. Now the voids are anything that's not in a solid particle. And we must remember that we would think, void means air. Void does not mean air. Voids is anything that's not solid. So voids can have water, they can have air, they can have some of both. All the volume of the voids, they take up volume, and they have weight. Both the solid particles have volume and they have weight. The voids have volume and they have weight. The volume of the voids includes all the volume that is not in the soil particle, either air, water, or the combination thereof. So therefore, we want to make some basic summations. And this is kind of like the summation of forces and moments you endured in statics and dynamics. The total volume is equal to the volume of the air plus the volume of the water plus the volume of the voids. The total weight is equal to the weight of the water plus the weight of the solids. If we're in an MKS system, the total mass is equal to the mass of the water plus the mass of the solids. The weight of any of those, whether that be air, water, or solids, is equal to the unit weight or density for if we're in an MKS system times the volume of that constituent. Now, to break things down a little bit, we have something called the phase diagram. And the phase diagram is illustrated. That, if we were to take a mass of soil and we were to, say, melt down all of the solid particles into a solid mass, you'd get a solid mass like that. And if we were to extract the water and we would put the water in one place, you'd have that. And if there's air left over, you would have that. And that's kind of the schematic representation we make for the phase diagram. And we could, in principle, use these equalities, and you see on the phase diagram on this side is the volume. We have volume of the solids, the volume of the water, and the volume of the air, and the sum of those two is the volume of the voids, and the sum of all these is the total volume. On the other side, we have the weight of the solids, the weight of the water, and the weight of the air, which assumes zero. And the sum of those is the total weight. Which is why these two equations don't have an air component to them. Now, we could theoretically use all these equations to solve everything. We won't do that because we'd like to take there's a lot of shortcuts we need to take, and there are reasons in practice why we try to refine things. Once we get this established, we can solve all the problems using that, and all of them are basically solved that way. But we we want to define some quantities that are related to them that we use on a regular basis. The first of those is the void ratio. The void ratio is equal to the volume of the voids over the volume of the solids. Not the volume, total volume. That's porosity. Porosity is the volume of the voids over the total volume. And so therefore, the void ratio and the porosity express the same physical reality, but they don't do it in the same way. And they actually can be related to each other. Those two formulas down here actually do relate the two. The porosity and the void ratio do have a relationship. There are a couple of other things. First is the degree of saturation. The degree of saturation is the portion of the voids which are filled with water. That is equal to the volume of the water over the volume of the voids. If all the soil's voids are filled with water, it is said to be saturated, and S is equal to 100%. It's usually expressed as a percent. The void ratio and the porosity are normally expressed as numbers, but the degree of saturation is normally expressed as a percent. And so, for example, if you have a soil where the voids are half water and half air, then the degree of saturation is equal to 1/2. The last one important is the specific gravity. You may be careful about this because it's easy to mess up. The specific gravity is the ratio of the unit weight or density of solids only to the unit density of water. It's only the solids. In other words, since there are, with most substances, we have a specific gravity or density, and we divide, we take the density, multiply with the volume, we get a weight, or we have a weight and we divide it by the volume, we get a density, and then we divide that density by the by the mass of water, we get specific gravity. In the case of the soil, we only apply specific gravity to the solids, not to the entire sample. So we don't think in terms of specific gravity of a soil aggregate, just the solids. And that's very handy for reasons we're going to see. Now, your book gives you some relationship between porosity, first of all, the summary of the index properties. We talked about all of these. We just talked about all of them. We also have some weight-volume relations. These are very handy, and you need to familiar yourself. There are three ways these are done. One of them is the unit weight relationship for the total. In other words, any soil will have the unit weight relationship for the total. And then the dry unit weight is when there's no water, and then the saturated unit weight when there's no air. And we see that which one of these you use obviously depends on the soil sample. If you have a soil that's completely dry or completely saturated, that simplifies a few things because you don't have to worry about the proportion of the voids being water, soil, or being either some water and some soil. If there's either all one or all the other, and we'll use those two in various ways as we go along. Unit system used in geotechnical engineering, and this is where things get complicated. I don't think they should be, but they do get complicated. First, we have weight and volume relationships. Most calculations are done in geotechnical engineering done on a weight basis. And it makes sense because most of what we do is static or pseudostatic. Usually, if we are interested in mass, we're getting into dynamics. And the normal civil engineer's reaction to something that moves is panic. And that's something we really don't want to do too much of. We try to minimize that in this course. But in any event, most of the work done is unit weight. The trout in the milk is the MKS units. I'll get that in a minute. With US units are the basic units or the pound or the kip. The kip is 1,000 pounds. You will also see US tons, which are 2,000 pounds, and a lot of your older tables and correlations are done on TSF or tons or US tons, and they're a nuisance. The kip is a lot more convenient. The basic unit length in soil mechanics is feet. You will see me write PSF instead of pounds per square foot and PCF instead of pounds per cubic foot. that is a shorthand you will see in your homework, on tests, and on the slides. It just gets used to it. Then there are your SI units. Technically, they are the official system everywhere else. The basic units of weight are newtons or kilonewtons, and the basic unit length is meter. The basic unit length for pressure is, one thing you'll see me use is kPa, pascals, which is a newton per square meter. You'll see me use that a lot. And our kilopascals, 1,000 newtons per square meter. You'll see that quite a bit as well. The complicating issue, and the only reason why I bring it up is because you do see problems like this on the FE exam, is MKS units. In many of these so-called metric countries, they didn't get the memo on the use of force-based unit system. So they have they have their basic mass is a kilo and mass unit length is a meter, and they do it by mass. And you'll see some problems like that. The bad part about using MKS is you have to constantly be fooling with gravity when you get into effective stress calculations, which is a nuisance, because the self-weight of the soil is one of the main causes of stresses in soils. Specific gravity and density. The unit weight of the water is 62.4 PCF, or 0.64 KCF, or 9.1 kilonewtons per cubic meter. Those are the most common things in the unit weight systems. For density of water, it's the one you're not going to. Slugs is something we leave that for fluid mechanics. The one you're going to be concerned with is 1,000 kilograms per cubic meter, which is very common with MKS type of calculations. Obviously, that sets us up for the specific gravities, which are basically the density or the unit weight over the density or unit weight of water. For most soils, the range you see in nature is fairly narrow. It starts down at the bottom. Quartz sands are about 2.65, and then you sometimes you'll see lower than that, but most of the time it goes up with the clays at 2.7 and above. It's fairly narrow, which is amazing in many ways, but it is. And you see that in these. You'll see that quite frequently. In some cases, there is a specific gravity test which you may or may not run in your lab. It's a little bit tricky to run to get that, and so because obviously getting the volume of that is the hard part. The mass is easy. The volume is the hard part, and it's fairly narrow. The one big outlier is your organic soils, which are always the outlier. All right, let's go through some examples. First example, we've got a total volume of 1 cubic foot. The total weight is 140. In that 1 cubic foot is 140 pounds. And the dry weight is 125 pounds. You get from a wet unit weight to a dry unit weight most of the time by either putting it in an oven, either a conventional oven like we use in our lab, or a microwave, and getting rid of the water, then a dry weight. You want to find the water content, the wet unit weight, and the dry unit weight. Okay. By definition, if you've got 125 pounds of something in a cubic foot, then the unit weight of it is 125 pounds per cubic foot. How about that? Same thing with a wet unit weight. The total unit weight is 140 pounds per cubic foot. If the volume were different, then you would just simply divide by the volume. The weight of the water is the difference between the total unit weight and the dry unit weight. And that's true whether the sample is saturated or not. So therefore, you simply say the total weight is 140 is equal to 125 plus W. And we're going to use the basic equations. And that means the weight of the water, subtracting those two, is 15 pounds per cubic foot. Now we take that. The water content, by definition, is the weight of the water over the weight of the solids. That's important because, it's tempted to have the weight of the water over the total weight. No, it's the weight of the water over the weight of the solids. And that's simply equal to the weight of the water over 125 because the dry unit weight is the total weight of the solids. So 15 over 125 is 12%. And that's your first problem. The next issue, we're going to use the MKS system. It can, in years past with this problem, I converted this over to true SI unit weights. We're not going to do it that way this time. Total mass of a sample is 18.18 kilos, and the total volume is 0.009 meters cubed. You just look at me and you say, is he kidding or what? Well, he's not really, but that is the weight of a standard, that is the volume of a standard compaction mold, which we'll talk about when we get to, ready, wait for it, compaction. And the dry mass is 16.13 kilos, and the specific gravity of the solids is 2.7. Find the wet unit weight, the dry unit weight, the void ratio, the water content, and the degree of saturation. That's a lot. First, compute the mass of the water. Is equal. One of the problems you run into is knowing where to start with problems like this. So the total mass is equal to the mass of the solids plus the mass of the water, like we said in the beginning. So we subtract the total mass from the dry mass to get, just like we did in the last problem, to get the mass of water, 2.05 kilos. And then we compute the water content by dividing that by the mass of the solids, or the dry mass, to get 12.7%. That's our first thing. The volume of the water, okay, that's the first thing. So now we've got the unit, we know how much water, and we can actually now compute the volumes, all the volumes. Volume of the water is simply equal to its mass divided by its density. That's pretty basic fluid mechanics, or even solid mechanics as well. So you take 2.05 kilos divided by 1,000 kilograms per cubic meter, you get 0.00205 meters cubed. There are certain things in life that MKS is really inept at handling, and volumes in this range, in small inches of 0.009 cubic meter mass is really not tiny, but it's not really, it's not large, but it's not tiny either. And you get that. One remedy to that we use in some lab experiments is to use CGS units, which I'm not going to go into. I'll leave that for the lab. The volume of the solids is basically computed exactly the same way, except that we've got to figure out what the basically the unit weight of the solids is. You take the total mass divided by the density. The density is the density of the water times specific gravity, and that's where we come in with this little quantity. So 16.13 is the dry mass, or the dry mass, or the weight of the solids, divided by 1,000 times 2.7, which gives you 0.00597 cubic meters. And the last thing is the volume of air. The volume of air is equal to the total volume, basically is what's left over. The total volume is equal to the volume of the water plus the volume of the solids plus the volume of the air. You move the water and the solids over to the right-hand side, and you get the volume of the air. So it's 0.009, total volume, minus the two volumes we just computed, and the volume of the air is 0.00098 cubic meters. Now, wet density. Wet density is simply equal to the total mass over the total volume. The total mass is 18.18 divided by 0.009, or about 2020 kilonewtons per cubic meter, which is, good, decent range. Compute the dry density of the soil is equal to the mass of the solids over the total volume again. Mass of solids is dry unit weight. We use that again, and we get 1,792 kilonewtons per cubic meter. The void ratio is equal to the volume of the voids or the volume of the solids, or the volume of the water plus the volume of air, because if you recall, the total volume of the voids is equal to the volume of the air plus the volume of the water. So we simply put those figures we computed down over here, over there, and we divide those by the volume of the solids, which we also computed over on this side, and we get a void ratio of 0.507. And the degree of saturation is equal to the volume of the water over the volume of the water plus the volume of the air. If VA is 0, S is equal to 1 or 100%. In this case, we know the volume of the water, we know the volume of the air, we take the volume of the water, and we just divide those out using this formula, and we get 67.7%. And that's how we do that. Example 3 kind of kicks us into a new dimension, so to speak. We have a saturated soil. Void ratio is 0.45, and the specific gravity of solids is 2.65. I haven't given you any volumes. I haven't given you any weights. I haven't given you anything. Just three-dimensionless figures. S is equal to 100%. Notice, find the wet unit weight and the water content. We have to make a few assumptions. First, that there's no air volume. That comes from the given. Saturated soil means that there's no air volume. Second, the total volume, which is unity, is whatever units I pick, it's going to be unity. The volume of the solids plus the volume of the water is equal to 1, because the volume of the air is equal to 0. And the last one is the unit weight of water is 62.4 pounds per cubic foot. First, we solve for our volumes. That's, and the void ratio is equal to the volume of the water over the volume of the solids. And that is equal to 0.45. Now, this is a little tricky. I don't really go through the math, but basically what you would do is you would say that to solve this problem, that the volume, you could basically there's a couple of ways to do it. Is basically what I'm going to do is I take this equation right here and that equation right there and solve them simultaneously by some method, whether it's substitution or whatever method you pick. That's how you do it. And you end up with the volume of the water is 0.31 cubic feet, volume of the solids is 0.69. As you see, they add up to unity, which means you haven't made a mistake, at least not in that kind of mistake. Okay, that's the first thing. So now you've got the two volumes. Then you compute the wet unit weight. The weight of the solids is equal to the unit weight of water times the volume of the solids times specific gravity of the solids, which you now have you are armed with all three of those properties. You simply plug and chug 114 pounds. We're using a cubic foot volume because we picked it, which means we're going to get some pretty good sized weights. We normally, in laboratory use, we normally don't use that big of a sample. The weight of the water is equal to the gamma W times the volume of the water. We know the gamma W times the volume of the water. We just simply multiply those two. We get 19.4. The total weight is the sum of those two, and it comes out to 133.4 pounds. In other words, the weight of the water plus the weight of the solids is equal to the total weight, whether the sample is saturated or not. And then I turn around, I compute the water content. Now that I have both the weight of the water and the weight of the solid, I just divide the two and I get a water content of 17%. And I'm done. Now the last problem we're going to look at is a well-graded sand. Well, we talked about what that was, but actually the gradation doesn't have any influence on its properties. Center of gravity of solids is 2.65, typical sand. Void ratio 0.57. Porosity 36. By the way, if you state void ratio, you've stated porosity, and if you state porosity, you've stated void ratio. We use one or the other in geotechnical calculations depending on which one is more convenient. For example, in consolidation, we'll use void ratio, but we may use porosity. Some methods for capillary rise, for example, use porosity. So it's just a matter of custom and convenience. Find the wet. Again, we got a situation where we've not been given any units. Nothing. We're just given a bunch of dimensionless ratios and told to find the unit weight of the salt. It's been told saturated. If you don't say it's, we could have said also that the soil had a certain degree of saturated, but it's fully saturated in this case. Okay, we'll set the sample volume in a foot cube. We'll work in U.S. units. The total volume, 1 is equal to the sum of those volumes. We're going to use porosity to compute the volume of the voids. And the reason why is it's quicker. Again, this is an example. I just mentioned the fact that I just mentioned the fact that we have that we use void ratio porosity, which is easier. In this case, porosity is easier. In this case, porosity makes more sense to use because we have porosity makes much more sense to use because all I have to do is because porosity is based on the total volume. And I know what the total volume is. So I have the total volume, the volume of the voids of the total volume, 0.365 times 1 is 0.365 cubic feet, which means the volume of the solids is what's left over. And that's true for saturated and unsaturated samples as well. It's 0.635 cubic feet. Now the saturated part kicks in because the volume of the voids is equal to the volume of the water plus the volume of the air. Since there's no volume of the air, the volume of the water is 0.3 is the total volume of the voids. So the dry unit weight is simply the weight of the solids is equal to the gamma of the water times the specific gravity times the volume of the solids, and I put 62.4 times 2.65 times 0.635 is equal to 105 pounds per cubic foot. That's the dry unit weight. That's just the weight of the solids. The weight of the solids and the dry unit weight are the same. The weight of the water is equal to gamma W times the volume of the water, and that's just 62.4 times 0.362 is 22.6. And the wet unit weight, therefore, is the sum of those two, or 127.6 pounds per cubic foot. Now we come to relative density. Relative density is something that we normally only consider when we have granular or cohesionless soils. We normally don't talk about relative density with cohesive soils. And Vroyd has an interesting discussion of what this really means. And the figure here in the corner is the encapsulation of that discussion. Okay. If we had a cubic array of spheres, and a lot of theoretical discussions of soil particles always start with assuming they're spherical, which they're not. I could, through the application of solid geometry, if I had a cubic array, I could compute the volume of the voids if they're stacked this way. In other words, they're stacked end to end up in this column and this column and this column and this column, this row, this row, this row. They're nice. That is the loosest state. In other words, that is the state that's going to have the largest volume of voids, or the largest porosity, which is the volume of the voids over the total volume, and Voigt uses porosity in this case. And that porosity can be computed from solid geometry about 0.4764. Now, if I were to take and shift things around a little bit, they have the densest arrays, where now you've got a situation where this sphere touches these two, and this sphere these two, and these two, and all that. The densest packing is equal to 0.2595. Again, using solid geometry. If all solid particles were spherical, this would be a lot simpler deal. They're not, and it isn't. But that gives you an idea. In other words, particles can be packed differently. In other words, and we kind of know this, just from experience, that you can shake something up and the volume is going to decrease. So we have a thing called the definition of relative density, and basically the definition of relative density, and we in the U.S. normally express it in terms of void ratio, although you could express it in terms of porosity, and it's also done frequently in terms of unit weight. In terms of dry unit weight. It is equal to the maximum void ratio of the loosest state minus the current whatever void state you've got over the maximum of the loosest state minus the E of the densest state. And that's the definition of relative density. So obviously you have to determine what the loosest state and the densest state are. There are experimental ways of doing that. So let's give an example. Sand backfill, unit weight of 109 PCF, water content of 8.6%, specific gravity of solids is 2.6. Find the void ratio and the relative density. And the reason why, now we could, if we had a formulation that was based upon dry unit weight, we could find dry unit weight. And so, first of all, we're going to assume VT is equal to 1 cubic foot. Thus, WT is 109 pounds. So we do the weight balance, and I've kind of taken a little shortcut there. I did not solve for the water content is 0.086, and if I solve those two previous equations, in other words, again, this is another thing where you basically have two equations, two unknowns. If I solve those, I'll get a weight of the solids of 100.4 pounds and the weight of the water of 8.6 pounds. That's why I had, so therefore I'm now in a situation where I know what my weights are. Now I got to know what my volumes are. My volumes are, and based on those weights, the volume of the solids is equal to the weight of the solids divided by the unit weight of the solids, which is equal to the weight 100.4 divided by, I was given specific gravity over here, so I know that 2.6 times 62.4, I end up with a volume of 0.618 cubic foot. The volume of the water is equal to 0.138 cubic foot. Honestly, the volume of the solids is equal to the total volume of the air. Actually, is equal to the volume of the total volume minus volume of water minus volume of solids, and I've got volume of water, air, and soil. To be honest, I don't really need to compute the volume of the water or the air. I just did put that in there just to give you another example of that. But the truth of the matter is, all I really wanted was the volume of the voids. And the volume of the voids is simply the two, water and air, put together. And I divide that by the volume of the solids, and I get the current void ratio. That is the void ratio of the soil in its current state. And once I get that, I simply plug and chug. I've been given Emax, I've been given Emin, I've been given the void, and I just plug in there, and I get a relative density of 14.4, which is kind of on the low side of the possibilities. It's kind of on the loose end. If we're up 60, 70%, it'd be on the dense end. Now, I said that relative density is mostly used with cohesional soils, and this is an example of that. You will recall the last time I talked about the SPT test that the relative density that you've got N values right here, and very loose, this correspondence. We'd already looked at that. Now I can, this, very loose means relative densities from, say, 0 to 0.15, and then loose 0.15 to 0.35, and then medium 0.35 to 0.65, and so on. If I say a soil is medium, it probably has a relative density of about 0.35 to 0.65, for example, and we probably saw a corrected SPT value of 10 to 30. So therefore, that kind of, if I take an SPT test and I apply the, and I use that to give me an idea of what's going on, what happens is with SPT, I can, my relative density, I can get an idea of what relative density should be. Now, it's not written in stone. These are empirical. These are first cut type of values. The angle of internal friction, which we'll talk about that later on in the course, you can estimate that. And last but not obviously, the range of approximate moist unit weight. The tricky part there is defining what moist is, but that also gives you an idea of what unit weight you can expect. So, in any event, that is that now you see the SPT values are already helping you to figure out what the other properties are for the purposes of calculation, if any other data not being there. And so, until next time, thanks for watching, and God bless.